Welcome back. We're at the last section of chapter 14 on acids and bases, and this is the section on buffers. Buffers is extremely important. It's a little tricky to understand, and we'll spend as much time as you need to in class to grasp this. But essentially, buffer is a way to stop huge fluctuations of of something becoming very acidic or very basic, especially in a body system. So we've mentioned before that the bloodstream has to maintain a very narrow window of pH, and if there is any fluctuation of even a little bit, it could set all of your body systems into chaos that could end in your quick and painful death. So this is one way that your body does constantly to stay alive is that there's a whole series of buffers in your blood. So what is a buffer? Okay. If if you were to have a glass of water and you added some acid to that water, you would have a very quick drop in pH. You would end up with a very sudden low pH because you have lots of acid in the water and very little base in the water to neutralize it with. Likewise, if you were to put a base in water, if you would put some drain cleaner or something in a glass of water and then took the pH, you would have an instant raise in pH and you'd have a very high pH in the water. So a buffer is a way that if you were to introduce an acid or a base into that system, it doesn't have as huge a swing. It will only change the pH by a very small amount, even if you had a sudden influx of acid or base. And it's pretty brilliant how it works. It's gorgeous. Okay, I'll try to explain. 7.4 is that magic number in the blood I told you about that you are trying to maintain in order to keep your body systems going. It's a very narrow. I think something like two or three uh, decimal spots, like point two or point three, is enough to kill you one way or the other. So the components of a buffer solution, I need you to memorize this, is an acid-base conjugate pair. If you recall, if I have an acid, right, let's imagine that I have hydrochloric acid, HCl. The H is what's going to be donated when it's being used as an acid. An acid donates a proton. What's left over at the end is that chloride ion, Cl minus. Okay, so the acid is the hydrochloric acid. The conjugate base is that chloride ion. Okay, so the components of a buffer are either the acid with its conjugate base, okay, or a base with its conjugate acid. So if you remember, if water is acting as a base and it takes a proton, it accepts a proton, and now that proton makes it hydronium, the hydronium is the conjugate acid. Okay, so if you have an acid with its conjugate base, so for instance, here's an example, it can be a weak acid and the salt of its conjugate base, or it can be a weak base and the salt of its conjugate acid. Right? Now, it must be weak because what's happening is that you don't want all of this acid to dissociate because that would change the pH. Remember, you want essentially to save up so that if you add a base, you're going to have some acid there to neutralize it. And if you add an acid, you're going to have some base there to neutralize it. That's what a buffer does. It's always against whatever's coming at you. So if you are adding acid to the solution, you want to have both an acid and a base in it, but you don't want the acid and the base to neutralize each other. That's the key. And I know that may not make sense to you. I'm so sorry. But if you were to have a strong acid and a strong base, those two would neutralize each other. So I don't want a strong acid and a strong base, but I want an acid in the water in case you have a base there. If you have a base added, the acid can neutralize it. I also want a base in that water so that if you have an acid that comes in, that base can neutralize the acid. but I do not want the acid and the base to neutralize each other. That's the key. Okay, so what we want is we want a weak acid and the salt of its conjugate base. And we want a, or it would work just the same. We could have a weak base and the salt of its conjugate acid. Okay, so typically we have an equal concentration of a weak acid or base and its conjugate salt, right? So here's some examples. Acetic acid, remember, was vinegar, is a weak acid. So if you were to say, okay, what is the salt of that weak acid? So let's look at this acetic acid. Here's the hydrogen that's coming off. That's making an acid, right? So if it comes off, what's left over? The acetate, C2H3O2, the acetate, -1. Acetate is the conjugate base of acetic acid. Okay, so this is a base. It could receive a hydrogen, and then here's the hydrogen that's going to go with the water to make hydronium. So this is acting as the base. Here's the acid. Here is the conjugate base, okay, left over, and then this is the acid that's made out of the water. Okay, so if you were to put acetic acid in the water, mostly you're going to have acetic acid with a little bit of hydronium, okay, because it's a weak acid. So you're not going to have tons and tons of hydronium. Mostly you're going to have this acetic acid hanging out as molecules, but you are going to make a little bit of its base. If I add a lot of acetate ion, okay, so that it's a base, that's not going to change very much of this back and forth because it's exactly the same. In fact, it's only going to make more acetic acid because that's, remember, Le Chatelier. This is going to drive the reaction backwards just a little bit. So you're still going to have some acid there. So if I added some base, this acid could neutralize it. Okay, but you're also going to see that if I add so if some acid comes, I'm going to have some acetate ion to neutralize the acid. And if I add some base, I'm going to have some acetic acid to neutralize the base. So what you're going to have is if you have both an acid and the base of that weak acid, you're going to have both of them in the water that don't react with each other, but can react with an acid or a base, either one that you can put in the solution with it. Okay, the sodium acetate salt produces sodium ions and acetate ions. Okay, so if I were to have sodium acetate, this is a salt of the conjugate base of acetic acid. So here's what's left over when acetic acid breaks apart. Well, if I have a salt made out of that, and I put it in the water with the acetic acid, then I'm going to have lots and lots of this base and lots of this acid. So I have a large amount of acid and a large amount of base, but these two are not going to neutralize each other. So what's going to happen is I have a storehouse of acid in case you add some base, that acid can neutralize it, and I have a storehouse of base in case you add some acid, I can neutralize it too. So the function of acetic acid in this example is to act as a buffer in case you add base at me. If you put some base in the water, the acetic acid, okay, I add some base, the acetic acid drops, and I'm going to make the acetate ion as a result. Okay. Now this is going to go up a little bit, but it's not going to go up as much as before. If you just had a glass of water and I had a hydroxide, it's going to go up 5 or 6 points. But if you have a buffer in it, it might go up a little bit, but it's not going to go up a lot. So it basically acts as insurance against a rapid influx or of base or acid. Here's the opposite. The function of the acetate ion is to neutralize any acid that you add to it. So if you add some more acid, this is going to react with it. You're going to end up with some more acetic acid, okay? But the acetic acid isn't as much as what this would have done to the number if you were just put it in water. Okay, so it's going to reduce the effect of it. So going back to this first picture that we had, if you add acid to pure water, you might drop it 3 full points, 3 full pH points, or raise it 3 or 4 pH points. But if you put it in a buffered solution, you might only drop it 0.1, like a tenth of a point, because the extra base that's in there can react with any acid that you add, and the extra acid that's in there can react with any base that you've got. Okay. So here's a summary. The buffer action occurs as the weak acid neutralizes any added base. Okay. And the conjugate base buffer in the buffer neutralizes any additional acid that you add. And it maintains the pH. So the pH does rise or lower a little bit, but it's not going to do it as drastically as if you did not have the buffer in the solution. Now, if you're going to find the pH of a buffer, all you do is solve for the acetic. I'm sorry. You solve for the hydronium and then take the negative log of it. That's how you find the pH of anything. You take the acid, take the negative log of that acid, and that's the pH. So if you can solve for the hydronium, you can find the pH. So here's an example. The K-sub-A, remember, expression was the constant that told you how acidic was it. Is it a strong acid or a weak acid? And if you had a large K-sub-A, then it was going to be a strong acid. If you had a low K-sub-A, it's going to be a weak acid. So remember, here's your formula, or here's your balanced equation. You have the weak acid put into water, and so it's going to be mostly molecules with a little bit of ions. So you're going to have a little bit of hydronium plus its conjugate base. And your K-sub-A is usually going to be very low because mostly it's going to be the weak acid stays its acid. Okay, so to find the K-sub-A, it's the 2 on the right. So the concentration of hydronium times the concentration of the conjugate base divided by the weak acid. Now you ignore water because it's liquid. Now, if you could solve for this hydronium, so you'd have to get the weak acid on the top and the conjugate base on the bottom. See here, so you've got hydronium concentration equals the constant, the acid constant, times weak acid over conjugate. All you're doing is solving for hydronium. And then whatever that hydronium is, whatever that number is, take the negative log of that, and you've got the pH of that buffer. Okay, so here's an example. The weak acid, okay, this is hydrogen phosphate, or it's the phosphoric acid, in a buffer of its conjugate base. Okay, so you've got its conjugate base there. Okay, that's its HPO4 is its conjugate base. Has a K-sub-A as 6.2 times 10 to the negative 8. Okay, it's weak, so it's going to have a very low acid constant. What is the pH of the buffer if it is 0.2 molar, if the concentration of these guys are both 0.2 molar? Okay, so here's what we've got. We've got phosphoric acid put in water. We're going to ignore the water. It breaks apart into HPO4-2. This is its conjugate base plus the acid. Right? So your K-sub-A is your acid times the conjugate base divided by the weak acid. These are concentrations. You ignore the water. You're going to solve for the hydronium. So this goes on the top. This comes on the bottom. So you have hydronium equals the acid constant times the this is the weak acid, and this is the conjugate base. And it said that this was 0.2 molar both. The weak acid and its conjugate base were 0.2 both. Okay. You also know that the acid constant is 6.2 times 10 to the negative 8. So you've got, here's its hydronium equals that number, 6.2 times 10 to the negative 8, times 0.2 over 0.2. This goes away. Okay, so you end up with, here's the concentration of hydronium. Well, what's the pH then? Take this number, take its log, and then change its sign, and you end up with 721. So I can find out what the pH is of a buffer solution. Now, the point is, you've got if you add an acid, okay, if you add an acid, it's only going to change a tiny little bit. It'll get a little more low, but it's not going to go drastically low. And if you add a base, it'll just go up a little tiny bit. It won't go up a drastic amount. That's the whole idea of a buffer. Okay. So we're going to do a lot of examples in class of this. We have to do this on the board. We have to play with this. Otherwise, you'll go crazy. But I hope this helps, and you can watch it as much as you can and see me in class.